Okay, so I think everything should be okay now. Okay, yeah.
Good morning.
Yeah, so yeah, I'm recording this meeting again. Thank you for coming back. And today we are going to look at a planar structure, like a patch antenna. So what we can do, this is what is our plan. So not to get too close to what you have to do in your project, we're going to look at a multi-layer patch antenna, okay? Patch antennas can be fed in different ways. For example, as you know, patch antenna is a very special metallization, rectangular metallization on top of very special dielectric. And I'm being sarcastic. This is a dielectric, and this is a rectangular patch. Have you studied patch antennas yet?
Not in this class.
No. Okay. So a patch antenna basically, how can I explain it? Okay. Let me just say this is PC for now. Okay. So it's a rectangular patch, and you will study it, but when you excite it is at a certain way. For example, if this is the length of the patch, we're looking at this cross section like here, right? The current has to be zero in the middle. The current has to be zero at the edges, right? Because the metallization ends, the current ends. Now, if you look at the voltage, though, the voltage looks like this. Okay, just because when the current is maximum, the voltage is minimum, and something like that. Okay. Now, if you want to feed, so here, since Z is equal to VI, right? When I is minimum, Z is infinite, right? So at the edge of the patch, at the edge of this metallization here, we have input impedance of infinite. In the middle, since V is zero, this is Z equal to zero. This is Z equal to infinite. So let's say you want to feed this patch with a 50 ohm coaxial line, microstrip line, or many different ways that you can feed a patch. A microstrip line would be like this. You know microstrip lines, right? You would feed the patch with a microstrip line like this. Sometimes you might choose to feed it with a coaxial line, just like the cables from the wall, for example. So if this is the patch, then you would choose a point, make a via here, and then connect the coaxial line to here, right? Now, if the impedance of this microstrip line or this coaxial line is 50 ohm, which is a standard input impedance for many connectors and cables, you have to design the patch so that the input impedance of the patch would be 50 ohm as well. So somewhere between Z equal to 0 and Z equal to infinite, the input impedance becomes 50 ohm. Okay, so that's why we don't feed the patch right here or right in the middle. We feed it somewhere in the middle between these two. Okay, and that's why if you connect the microstrip line directly to the patch, this is not going to give you a good answer. Usually there are some papers that you would read for your project that you have to make some adjustments to the structure of the patch to make this 50 ohm. But anyway, so a very simple single layer structure for the patch would be feeding it with a microstrip line. And then in the bottom we have ground. In the bottom we have a PEC, so that no radiation goes in the back. We want all the radiation go to the front. That's why patch antennas are very good, because then it would make the radiation pattern kind of look like this. So it would radiate in at the front. This is the basic antenna that you can see even in your phone, for example, or many communication devices use either patch or something, a modified version of the patch, like PFA or things like that. But the basic comes back to this. Okay. Now, again, if you want to design this patch, you have to design it λ/2. And then you can go with a square patch λ/2. Since the radiation in this site, for example, if you don't have any specific beam width in mind in the two planes, a square patch should be fine. You can go with a square patch λ/2. And then the macro strip line should be like 50 ohm. Another way to feed a patch, which includes more layer, is if you have this dielectric, you have to patch in the middle of it. But instead of going with via, which is a can be complicated fabrication process, you go with a patch and then another dielectric layer. You put the macro strip lines here, then in the middle you make a slot here. Make a slot. So when you look at from the top, this is the patch. This is the kind of like modified ground layer with a slot in it. This is the second layer. I don't have different colors. And on the bottom, you have this macro strip line that would feed it. This is caused by coupling between different layers. That's how you're feeding the patch. So I was asked to explain this for you because it requires more, the geometry is more complex and you can see how it works. Okay, so let's do that. Then a lot of these things are based, the dimensions are based on experience and rough approximations, like formulas that you have. For example, for the patch, I'm going to go with λ/2, a square shape. For macro strip line, you can use any online tool to say, if I have a dielectric with this thickness, with this epsilon r, how much is the width of the macro strip line to get 50 ohm, right? That's how you calculate. So we're going to use that as well. And then for the slot, as long as it's a little bit bigger than the macro strip line, it should be okay. Some people go with λ/4, but you have to tune it. It's not, there is no definite answer.
So basically in the middle layer is the PC plane, and then you just get a slot.
Yes. Yeah, you make it slot. And then again, the position of this slot has to be somewhere between the middle of the patch and the edge of the patch for the same reason that we explained. Now there is an offset here. The macro strip line can go further. Again, this is something that you can play with to increase the bandwidth of your patch antenna, to make it match better to 50 ohm. It adds to the imaginary part of the input impedance. Okay, so let's just start with that. As there is not much to explain. Like a lot of these dimensions have to be tuned and optimized. So we just know that we want to go with λ/2. And let's say you were dictated, like your project, to go with a certain dielectric here. So your patch has to be on a certain material, and the thickness is kind of fixed. So you have H and epsilon r.
Yeah.
This is given to you.
Yeah.
So let's do that, okay? Okay. So I'm going to make another design here. So you can go back, insert HFSS design.
How about we get a Zoom link?
You want to join through Zoom?
Yeah,
Yeah, okay.
It's easier for us to see.
Okay, if you have a computer, yeah, true. So does everybody want it? Okay.
Can you hear me?
Here. Okay, I just made an announcement in the course, so you can access it. Okay. Now let me go back here. Okay, so now the size of the ground plane really defines how directive your patch antenna becomes. But again, I'm just going to go with a rough number like lambda or 1.5 lambda, something like that. Because these are, again, you have to have specifications in mind to design these things. So since we don't have it, I'm just gonna go with a random number here. So okay. So let's say this is our dielectric. Again, I made a rectangular box. I'm going to parameterize it. So let's say this is minus dx2 minus dy2. I have a thickness in mind, so I'm going to say it's 0. Now dx, I'm going to define it 1.5 lambda, for example. Then let's go with 10 gigahertz again. So lambda was 30 millimeter. dy again, I'm going to make a square. So this is again the same thing, dx of dy. And then the thickness of the substrate, I'm going to call it h, height. Now with height, I'll go with 1.5 millimeter. Let's say this is given to you, right? The material, the thickness of your substrate is given to you. Okay, so now this is my substrate. Now I want to assign a material to it, right? Usually dielectrics are given. Sometimes it's a standard material, like you want to assign material. So you go right click, assign material. You have a list of these different sub-materials. Usually for dielectrics, you might get your substrate from Rogers. So you can go through the list of all the standard dielectrics that exist in Rogers, like this. And then, or you might have to define a new material. Like you're not sure if the material that you're using is actually in there. So how do you do that? I'm not sure if for your project you have to do it, but in that case, let's just say you go add material. Let's call this my material. Now, you know the permittivity of your material. Let's say it's 3.4, for example. You have, if the loss engine is given to you, you can define it like 0.001. Okay, sure. That's a bit lossy, but okay. So usually these are the two properties that define the dielectric. Okay. And then remember that this frequency, and now we are saying this is the property of my material at this frequency, right? Sometimes you might have to define these as a function of frequency, like here. Anisotropic, tensor, nonlinear, we're going with a simple material. That's an advanced topic. But yeah, sometimes your dielectric constant might go down with frequency. So you have to define it as a function of frequency. Anyway, so now I define my material. I'm gonna assign it to this dielectric. Okay, and what else? Okay, now let's define the patch. So for the patch, again, I'm going to show you how you can define it as can you hear me? Okay, no, I can't hear you, Javier. Just 1 second. Can you unmute yourself, Javeria?
Yes, hi, can you hear me now?
Oh, wait. I think I know what's the problem. Actually, no, I can't hear you, Javeria. I'm not sure. Can anybody hear Javeria? You're muted. Maybe.
Oh, can you hear me now?
Yeah.
Okay. Okay. So I want to ask now, when you are defining the permittivity, this is the permittivity of the ground plane right now, or the copper that we are going to use as the patch?
This is the substrate. Yeah, this is the dielectric substrate. Permittivity, yeah, permittivity is defined for dielectric substrates.
Okay.
Yeah, we haven't got, this is only the material that we're going to etch the patch on it.
Okay.
I'll
In our project, we are given the copper, right, to put on the plastic ground plane.
Yeah, that plastic, that's a kind of dielectric, right? So that plastic, you have to enter its properties, like just like what we did here, here, and define a new material so that you can simulate this stuff with it.
Okay.
Yeah. Okay. So this will be your plastic, basically. We haven't gotten to the copper part yet. This is for now, this is the plastic that we are going to put those copper tape on them, basically. Okay, now let's go and
What were the dimensions again?
I went with 1.5 lambda.
Okay.
Yeah. Now let's go put the patch on this. Again, I would recommend starting with a sheet. That means just a surface without any thickness, but I'll show you how you can basically make this into thick metallization. This is just because since you're at the beginning, you're tuning, it takes less time for HFSS to solve this problem. Okay, now let's say px over 2 minus py. These are the dimensions of the patch. Now, the patch is going to be on top of the dielectric, and our dielectric went from 0 to h. So the z dimension of the patch is going to be h. Now, px is, I'm going to define it lambda over 2, or let's define it as an independent variable. You can define it as lambda over 2 is 15 millimeter. So I'm going to put 15 millimeter for now. Whenever you link a parameter to another one, it becomes a dependent variable, right? If I define px as lambda over 2, in order to change px, I have to change lambda. But sometimes I want to change px independently of lambda. So I define it, I give it a variable, and then it becomes an independent variable, basically, px and py. Okay, now let's look at it. I'm going to change the color here. Okay, so this is the patch now. Now let's make this the bottom layer, which is a ground with a slot in it. So for now, I'm going to go back here, make this transparent so that we can see stuff. Okay. Okay. So now for the ground plane, again, we have a complete surface, a rectangle, right? That we are going to subtract a slot from it. This is how it looks like. This is a complete PEC. Then a slot is subtracted from it. So it looks like this, right? So let's do that.
Do I show the dimensions for the patch again?
I put it at 15 by 15 millimeter.
50 by 50, right?
Yeah, almost lambda over 2 at 10 gigahertz. This is, I'm designing for 10 gigahertz. Now let's go back. So here, I defined the dielectric minus dx2 over 2 minus dy over 2. This is exactly going to be the size of my dielectric box, right? Because I want the whole dielectric on the bottom layer to be covered by this PEC. And then 0 dx dy. So now the ground layer came here. Just gonna select all this color for all the metallization. Now, if you look at it this way, the patch is on the top layer, the ground is on the bottom layer. Now we want to pick up put a slot in this ground. Now, for the slot, let's see how we parameterize it. So this is the patch, right? We want a position, let's say this is X, this is Y, this is X, right? Now, in Y direction, the center of the patch is at 0, right?
Yeah.
So in Y direction, it actually, let's say minus slot. Sorry, in X direction. In X direction here is at 0. So it starts from minus Sx over 2 to Sx over 2. For Y, again, we define an offset here because we know it's not going to be exactly at 0. I'm going to call this offset like offset Y, then minus the size of Sy, slot Y over 2, offset plus Sy over 2. So that would mean the slot size is going to be Sy, and then in Y direction, and then it's offset from 0 by some offset value, right? Now, how much is this offset? Rule of thumb, get it when you get a little bit of experience. If this is the length of the patch, which is L, then here is going to be L over 3. So that would mean that from 0, if you calculate it, the position would be L over 2 minus L over 3, which is almost L over 6. I mean the size of the patch. Don't worry about it. If you don't know, you can always start from 0, go to the end to tune it, right? I'm just giving you a couple of tips to optimize this faster. Okay, so now let's make this slot, basically. Again, I'm gonna make a rectangle and then work with it. So let's go exactly with what we said here. So we're going to go with minus Sx over 2 minus Sy over 2 plus some offset Y, I'll call this, plus, or offset this to define this as a slot offset. And then since we want this slot to be exactly on the layer of the ground, I'm putting 0, and then here Sx. So this is the dimension of the slot in X direction. Again, you can always optimize it. I'm going to go with almost half of the patch size. Patch size was about 15 millimeter. I go with 7 millimeter, for example. Sy here, Sy is important to be smaller than Sx, so that you would actually, when you look at it, it looks like this. The electric field or the magnetic field, sorry, in the slot would look like this. So we can go with almost like 1/3, 1/4, something like that. We can go with 2 millimeter, for example. Offset now, I said it's almost over 6, so L over 6, we went over 15 millimeter. For the size of the patch, over 6 is going to be almost 2.25. Yeah. Okay, now this is SX. This is SY. Now let's see where this slot ends up. Okay, so let's look at it from the top. So you see, this is where the slot is. Now we want to get, this is the ground plane. I'm going to change it to the ground, the name. Subtract this slot. I'll call this a slot here. From the ground. So again, we go ground, slot, and then operation subtract. Okay. So let's look at it here. It looks a little bit, maybe I have to change this color. Let's put it yellow. It's not very visible. So you see, this is exactly where the slot is. And then we are seeing the patch through it. And then from the top, this is where it is. Okay. So now let me call this patch. What else do we have? We have another layer where the macrostrip is. So since you only have one material, let's go with the same material substrate on the bottom layer too. So I can just easily copy this, go copy Control-C, and then Control-V. So now I'm going to call this top substrate. And then this one. Bottom substrate. So the bottom substrate, we wanted to start from -h to 0, because this is 0 to h. We want the bottom layer to go from 0 to -h. If again, you're dictated, you're given a material, then that's your substrate, right? So I'm going to assume that the thickness and the permittivity of your material is given to you, and it is the same as the top layer. So the bottom layer, the only thing you have to do, go here, edit it, start it from -h, and then the size is still h. So now it looks like this. So now we have 2 substrate layers. In the middle, we have the ground, and on the top, we have the patch. Now we want to design the macrostrip line to feed this. So let's look at it from the bottom here. So we want the macrostrip line, if you can just follow the cursor here, to come from the edge of the dielectric, because that's where you put your SMA, basically, SMA connector. Do you know how the SMA connector look like? So SMA connector. This is the SMA. This is called SMA connector. So you would basically solder this to the edge of the substrate to feed this macrostrip line. Let me show you a patch antenna. Here, something like this, for example. This is like a patch antenna. You see how SMA is connected through the macrostrip line to feed it. So we want to make the macrostrip line come to the edge, because that's where we can connect the SMA connector, basically.
Where does the slot look like physically?
The slot looks like, this slot looks like. Let me show you. Not something like that. I'll show you. So it's basically metallization that a metallization that part of it is carved out. You know, like a pumpkin. Basically, yeah, you take some part of it out, right? So if you have a like let's say a complete sheet of metallization and try to carve out a little bit of it, then that would be the slot inside that metallization. Let me show you, like maybe here on a real prototype, it would be more clear. Yeah, but something like this. Oh, yeah, here. You see, this is a slot here. You see,
Okay,
it's
thank you.
all of the material, it's a PEC or a copper layer, and then part of it is carved out to make a slot in it. And okay, so now let's go back. So now we want to calculate this macro strip line. Okay, we want to see what should be the width of this macro strip line. I'm going to go back here because I forgot what the material was. So the material, we said the thickness was almost, I think, 1.5 millimeter. And then the permittivity, you can always go back here, properties, look at it. My material, I said 3.4. So you can easily come here, say microstrip line impedance calculator. Just go with any link that comes up. So now dielectric constant, our material is 3.4. The width we don't know, the height is 1.5 millimeter. Now we want to see how much we should have the width so that the input impedance be 50 ohm. I'm going to put 1 millimeter. Let's see. 1 millimeter is almost 95. So as you know, in the macrostrip line, as you go wider, the input impedance goes down. So I'm going to go with 2. Now we got to 7 ohm. You see the impedance is written here. Then go to 3 millimeter. Almost, we're getting close, 3.5 or 3.4, let's say. Yeah, almost 3.45, for example. So this is our rough estimate, right? Let's do that. So we want to make, again, a rectangle here that goes from the edge to here. Oh, no. Like this. Now I'm going to, again, parameterize it. Let's call this macro strip line. Okay, the macro strip line starts from the edge in a y direction, right? In x direction, let's look at it again. In x direction, it has to go from minus widths over 2 to plus widths over 2. So let's call this minus widths of my macro strip line over 2. For in y direction, it starts from the edge of the dielectric, which we called it already dy over 2. And then since it is in the bottom layer, the z dimension would be minus h. Sorry, the z position. Now, as we said, 3.45 millimeter should be okay for the width. So I define that. WM y size. Now for the y size, again, we know it has to go after the position of the slot, right? So how can we define the y size? So let's say this is dy over 2. You started from here to here. We want to go from here to here. The slot has to be somewhere here. Now we can say that the length of this microstrip line, firstly, has to be, if this is the position of the slot here, which we call offset S, right? So it has, in the center would be dy over 2 minus offset of the slot, right? This is exactly this point. So this is part of the length of the macro strip line. Then we have plus the length and the size of half of the size of the slot, which is sy. I'm not wrong, sy over 2. Then we want some part of it to go out of the macro strip line. Let's call this the offset of the macro strip line. So this is how we define the length of the macro strip line. Again, trying to parameterize everything. So for now, I'm going to call it LM. And then when it asks me what is LM, since I started from plus, I go minus. The size, I go to the minus direction, minus LM. LM is dy over 2 minus offset s plus sy over 2, and then plus some offset. I'm going to call this the offset of macro strip line. That's the only thing. I think I defined the offset, but it's okay. Offset M is not defined. I'm going to just choose a variable 1 millimeter here. We'll see what happens. So now this is what the macro strip line looks like. Now let's look at it from another perspective so that everybody can see how it looks like at the end. Change the ground here to add some transparency. Okay. Okay, so this is on the bottom layer, we have the macro strip line. In the middle layer, we have the slot. And then on the top, we have the patch, right? Okay. Now what is left? The geometry is done, right?
Excitation.
We have excitation, we have the boundary condition, defining where is this patch? Is it in water? Is it in air? Where is it radiating, right? So remember, whenever we have a radiating element, we want to define a box of vacuum and then say, this is my radiation boundary condition, right? So since we already know this, I'm just going to quickly make it an air box here. Not repeating myself too much. So again, I remember that I have to stay away from the edge of my structure by lambda over 4. Then this is okay. So I want to see inside of it. So this is my okay. So now we haven't said anything about this ground. You see this on a sign? That means that these sheets are not specified as perfect electric conductors or copper or anything. So I'm going to assign boundary conditions to them, define them as PECs. So assign boundary perfect E. You can go one by one or you can assign them all at once. Doesn't make any difference. So if I show like boundaries here, perfect E, it shows all of the metallizations basically. Now we have box A. This is, I'm going to call this air box here just for clarity. So air box, I'm going to call this or add a boundary radiation to it. Okay, so now this is the radiation. The metallization is okay. My material is okay. Now we have to excite this, right?
Yeah.
For excitation, again, I would suggest using a lump port, or actually this is what you have to do here. You say my input impedance virtually looks like a 50 ohm lump port. And then where does the excitation go from? If you have a macro strip line here, so basically what you do is that, this is a bit harder, but basically you go, let's look at it from the side here. So this is where the macro strip line is. This is where the ground layer is with some slot in it. This is where the patch is, like this, right? You want to go from the excitation, we want to go from the macro strip line to the ground. This is where the positive signal goes in, and this is where basically your zero. So we define the lump port, as you know, we saw it yesterday in the same way, and then say that it goes from the macro strip line to the ground. Yeah.
Is reversed.
It will go from the ground to the macro strip line.
Yeah, the ground plane is 0. Maybe I'm wrong.
Because when you have a positive, let's say here, and you have a negative or lower voltage, the electric field goes from here to here, right? Doesn't make any difference, but you can try it. Doesn't make any difference, but physically it should go from the where the positive signal goes, or where the signal is, and to the ground. Okay, so again, we want to go to the edge of the structure here and move on the XZ plane basically, and then assign this lump port. So I'm going to change this to XZ in visibility, and then basically draw this. So I know the lump port it has to be exactly to the size of the macro strip line, and the width of the macro strip line is, I define it WM over 2. In Y direction, it's DY over 2. In Z, it goes from minus H to H. X size is exactly the macro strip line size, and this is H. Okay, so now you see this is our going to be lump port. We call this lump port. Let's zoom in on the lump port here. Okay, let's assign the excitation. Assign excitation, lump port. I'm going to define 50 ohm, and then because that's my SMA connector indicated by the SMA connector. 50 ohm, then next normalize it to 50 ohm, and then
Yeah.
done.
Another question. Like, what's the difference between normalized and non-normalized?
So S11, when you define it, has ZL minus Z naught, right? When you say normalize it to 50 ohm, in that 50 ohm is going to be used in S11 calculation to calculate S11 for you. If you don't normalize it, then what is your S11?
It's you normalize and you don't normalize, you have different S11.
Yeah. Now, okay, so the excitation is done, the boundary is done. Then we go again for analysis. Let's go add the solution setup. If you remember, we're going to go with 10 gigahertz. Increase this as much as we can, and then options, have a couple of converged cases like 3. Minimum, I just put 5, for example. We'll just put here iterative solver for quicker answer. Go 5 to 10 and 15 gigahertz, 101 with 100 megahertz resolution. And then we go here, radiation. We want to look at the radiation pattern. So let's go to the infinite sphere again, minus 180 degrees. So these are all similar to what we did yesterday. Now, let's run this. Let's see how it looks like. How the S11 looks like, how the gain looks like, directivity and things like that.
So if you don't normalize, you still have S11. So what that S11 represent?
I don't know, I have to check. Yeah.
So, I'm just
Yeah, I have to check.
curious.
Yeah, I usually normalize because like it makes sense to normalize. I think we set up everything correctly, but we'll see.
What's the first speed?
5 to 10, 5 to 15. So we're getting ready. So let's prepare our reports. Here we want to look at S11. We want to look at input impedance, real and imaginary. Then we want to look at, these results are not ready yet. It has to update it once it's done. And then we can look at the far field here. We can look at the gain and directivity on the same plot. No, it doesn't let us go to the same plot. But gain in dB, we can look at the two planes, like phi equal to 0 degrees, and then 0 degree, and then 90 degree. And this is this. Then we can also look at the gain in polar shape. Or yeah, 3D, sorry, 3D polar. And then dB here. Obviously something is very wrong here. Our design is not optimized. Has yours solved it already?
Yeah.
I don't know what's up with our server.
Oh, that was really fast.
Let me see. Okay. No, but your S11, how does your S11 match?
I plugged in.
It's way up, right?
I just plugged in random numbers. Like
Oh, you didn't do this number.
I missed some of the numbers you
Okay,
you
okay.
put up, so I
it's-
just put placeholders.
Okay, okay. It's fine.
So if it worked, it would have been really lucky.
Yeah.
Nice, but lucky.
Like the microchip goes right to the center, the long port, or the slot right to the dead center.
Okay.
Actually, no, I think I put it off by 2 millimeters.
Okay, we don't have to wait for this, so let me just. How can I remove this thing? Oh. Okay, so here. I have this basically. Yeah, I already optimized this, so I'm going to show you here. So you can see like for different parameters here, for example, I optimize it as the offset of the microstrip line or the position of the slot. And then at the end, it looks like something like this. If I go to the bottom, you see it. So something like this. So it is a bit more off. Then, sorry, I'm gonna just exit this. Then, yeah. So then when we look at the directivity, and let me just go back here. Offset is 1 millimeter px. One millimeter px is 2.5 millimeter. So this should be better. Then we can go and simulate this again. So now if I plot the far field for this case, look at dB. Ooh, all of these. So 0 and then 90-degree plane. The frequency is that one. WM. This is 2.5 millimeter, unless I don't know what was that one. Then this. Yeah. Okay. So it almost looks like this. So if I plot the polar, okay, yeah. Let's look at. So you can see that this is what the pattern of the patch look like here. Again, these are not exactly, I used 2 different dielectrics or things like that, but you can see. Obviously, we are going to have some radiation back from the microstrip line. This is a drawback of this kind of slot fed patch antennas, but it's okay. Then if you want to make the directivity larger, you can see that the portion of the patch and or the ratio between the patch and the substrate here is smaller than what we designed in the other project. So this is going to be less directive. So the larger the ground plane is, the more directive it's going to get, and the narrower the beam width. Now let's say these are just simulation that you have to do. Like, for example, you see in this design, it's almost this is ready. So this is the design that we already sorry, we just designed here. The resonance happens at 11.4. Again, this is because of the fringing fields. This is because our impedance is not exactly matched. The microstrip line value that we put was approximate and things like that. But let me show you one thing. Now, let's say I want to make this case more realistic, because I can never have PEC or sheets as metallization. So how can I make these layers to have thickness? Something super easy you can do is, let's say we want to add thickness to the patch. Let me go back here, change the design. Okay. So the patch, you go patch, edit,
you edit the surface, you thicken the sheet. Now, based on how thick is your metallization, it might be, for example, usually when you order dielectrics from a company, they come with two, they are covered on the two sides with metallizations. I could have brought like something, but then in the fabrication process, what they do is they etch those metallization to make the patch for you, right? But the thickness of the metallization on the two sides of these dielectrics is mentioned by the company. You can't go any arbitrarily thick metallization. Sometimes it's 18 micron, sometimes it's 36, or for like more regular dielectrics, it can even go higher. For now, I'm gonna say, like, for example, 0.36 millimeter, which is like 36 micron. So now my patch became a 3D body, and then now it has this metallization. Something you have to make sure is that sometimes it adds the thickness of the metallization goes down and sometimes goes up. Let's see how we can look for that. So here it did it correctly, you know. The thickness of the metallization has to go up from the dielectric, right? It can never go down. Like as you would put the tape of these copper tapes on your plastic or your dielectric, it would go higher than the dielectric. So this is good. But you can even make it minus, and then this would go down. This is not okay, but let's say you wanted to do this. For example, now that this is a 3D body, I can assign material to it. Let's add copper to it. Let's say this is copper. Okay, copper is here. It's already material. You can say this is copper. Good. Now it made a copper and put the patch here. Now let's go to microstrip line. The microstrip line is in the bottom here. Let's add metallization thickness to it. Go against surface, thicken the sheet, and then usually you have one, and now you can see that the positive made it go down. Again, you always want it outside the dielectric, so this is okay for us. You can assign copper to the microstrip line too. So now the ground is a little bit trickier because as you add thickness to it, it actually, whenever you have a layer in the middle, you have to actually separate the dielectrics, right? So I'm gonna add thickness to it, but if you want to be really thorough, you have to consider this thickness in the distancing between the dielectrics. I'll show you how. So surface, thicken the sheet, goes here. So now, so you see, now I have this. I have the first layer, which I said it starts from 0 to H. I have the second layer, the bottom layer, that starts from minus H to 0. Now in the middle, I have a second sheet that can't go to any of these layers, right? So if my first layer starts from minus H to 0, the second layer starts from the thickness of this on top of this. So if this is called H, let's say metallization, then the second layer has to start from HM, for example, and then go to H plus HM, and then this guy has to go to HM plus H2. Let's adjust this to make this more realistic. I'm gonna add copper to the ground. I'll show you how it looks like. So the bottom substrate, let's assume, is correct, and we're going to adjust the top layer. HM goes, HM is the thickness of metallization. So now you can see that the second layer starts from after the metallization to the top. The patch again, you want it to start from HM. So it moves up here. Now it looks okay. Because realistically in fabrication process, when you want to fabricate these things, the fabrication company would ask you all of this basically. If your stacking is off, they wouldn't understand what you're trying to do. So yeah. Okay, now it's a realistic case. You can, let's say you optimize everything and you want to just run things for a couple of last time. So to make sure everything is working correctly, now you can just run this. I'm not gonna run it, but because it takes time. But yeah, that would be the patch. Maybe just run it for one single frequency. Let's see this. Oh, this is not working at 10 gigahertz. It was too large for 10 gigahertz, but yeah, I'm just gonna show you while this is being ready how the simple patch with a macro strip line would look like. So again, this is not gonna be a good patch antenna because as I said, your feeding point should be somewhere here, not at the edge, not at the center. But when you connect the macro strip line directly like this, then what happens is that you're feeding it at the edge. What they do in a couple of papers is that they would go, well, let's say this is the patch. This is your macro strip line, right? What they do is that to make the macro strip line go to the position that they want, they would make the shape like this. So they subtract these two rectangles from the patch so that the macro strip line exactly feeds the patch with an offset here, not at the edge. Again, this lens is exactly like tuning the position of this slot. Okay. I think that's all from HFSS. You can ask me questions if you have, but I think that covers it for the project that you want to do. Any questions? Javeria, do you have any questions?
I'm just thinking that first we will analyze it for a single patch, and if we achieve the specs, otherwise we will go for an array, or this is it, like a simple patch
Yeah.
for the specs.
Yeah. Okay. I think that would give you the minimum things that you would need. You know, for example, here, if I look at the gain of this patch, yeah, the gain of this patch, this is too off though. Let me go back here. Let's see, look at this patch, for example. I already have the results, so. Oh, I don't have the results. Nice. For some reason, okay, yeah, this patch antenna, for example, it's very narrow band. For example, like a single patch that I designed here. It's very narrow band, right? If you go with the 10 dB bandwidth here between M3 and M4, then you only have 400 megahertz of bandwidth. And then also the gain, I think, is about 6 or something. So if you want to do minimum, yeah, obviously you can go with this design. But yeah, if you want to look at some papers to see how you can improve the bandwidth or how you can get a better gain and things like that, basically. You would have to get a little bit more creative.
But patch antenna is a very, or planar structures are very developed topics, so I'm sure like there are like a million papers on them that you can just take the design from them and just use it. Yeah, maybe I stopped sharing from here. Or sorry, stop recording.
And one thing I am